All right, thank you all for coming. I'm so excited to be here. I am going to tell you about the discovery of a hidden trove of massive black holes in dwarf galaxies. And this is our pretty picture of a real dwarf galaxy, but we did take some artistic license with it, such as adding a black hole that is actually obviously much larger than a real black hole. And the idea is to take this discovery, which was great fun for us, international news, and put it in context, because it's a little odd that somebody like me who's never worked on black holes or AGN before would have done this. So I also want to highlight that we have a wonderful team. This is my graduate student, the lead author of the study, Professor Chris Richardson, who is 30 minutes away from me at Elon, and two undergraduates, Ashley Bittner and Carlin Ferguson, who worked with me on this project in the beginning before the other two got involved. And then the Resolve and Eco teams, and I'll tell you more about those surveys and how they pushed us to work on this science. So I want to deconstruct my title, the discovery, the hidden trove, the massive black holes, and the dwarf galaxies, and then actually come back to our kind of rediscovery of what we found at the end. So I will just give you the plain old story of what we found at the beginning. I understand that there are people here who are interested in history and philosophy and not necessarily have the astronomical jargon, so I will try to make this a very minimal jargon talk, but please feel free to interrupt me if I slip. And then I'll talk about the statistics of this hidden trove. Why are we entitled to call it that? And the science context of both the black holes and the dwarf galaxies. So just as a little bit of background for those of you who don't study galaxies, our picture of galaxy evolution and the evolution of the universe is hierarchical, where small structures grow into larger structures. This animation is showing dark matter growing through successive mergers, but the notion is that within the dark matter, galaxies are forming and also growing through successive mergers, as well as in between mergers, periods of gas inflow. And those gas inflows feed the growth of galaxy disks through accretion, and that differentiate periods of violent growth and quiet growth that are alternating. I've shown that in this schematic diagram. This is a merger tree cartoon. Time flows downwards. So we start with the little branches represent little dwarf galaxies in the early universe. Every time a branch comes together, you have a merger and you form something, loosely speaking, that is round and at least temporarily a bit more gas depleted. So we show it as red and dead is kind of the jargon for something that is at least temporarily not forming a lot of stars, but then during the quiet periods in between mergers, gas flows in, you get accretion, you get disk growth. And so galaxy morphology is kind of alternating. And this is very loose in the sense that every time dark matter merges, there isn't necessarily a galaxy merger right then, because we have large dark matter halos with multiple galaxies within them, and it may take them some time before they merge. They may not merge in the age of the universe. So, there's some complexity there, but this is just kind of a cartoon picture of how we think about galaxy evolution. And within that, we have this notion that nuclear black holes grow with galaxies. Sort of, again, it's a cartoon picture, right? And so I put little dots in there to represent our black holes. And so from a cartoon point of view, we could say there's, again, a violent growth alternating with a quiet growth, where the violent is, what we probe with gravitational waves, the wonderful black hole mergers that we can now actually get evidence of. And that is alternating with feeding active galactic nuclei, which is mostly going to be gas accretion, but also stars can fall in or whatever. So that is kind of the same, loosely speaking, dichotomy, and you would therefore expect that the active galactic nuclei, which is most of still how we study black holes, right? Because the gravitational wave is just kind of getting going, that this part of it really should be possible to trace all the way through the merger tree. But historically, that hasn't been easy. We've mostly known about AGN in giant galaxies. We've mostly known about the end of the merger tree, so to speak. So how do we actually detect active galactic nuclei? How are they different from, say, hot stars, from a lot of star formation, which would also be fed by inflows of gas? Again, kind of a cartoon of the spectra of stars versus AGN, where from the radio through the X-ray, we see that stars are not as luminous on both the long and short wavelength ends. And this gives us the opportunity to detect AGN via their spectral differences. And in terms of my work, what we focused on is this end of the story, where we're looking at actually optical wavelengths, where the AGN should have a harder spectrum, meaning more short wavelengths in their spectrum. And so if you look at the gas emission, where one cartoon gas cloud here is being lit from the inside by an AGN, and the other one is being lit from the inside by young hot stars, you would see a difference in the spectra, where at the top we have an example of an AGN spectrum. At the bottom here is star forming region spectrum, and some of the differences show up in the actual emission lines, where we have excited gas emission lines of N2 and O1 being higher for the AGN. So here's O1 and here's N2 next to H alpha, and we don't even see the O1 for this ordinary star forming region, and the N2 line is lower. And those kinds of differences reflect whether we're dealing with a harder ionizing spectrum or a harder radiating spectrum, such as we would get from a black hole, an accreting black hole. So the classification system based on these lines before our work looked something like this. This is kind of the prevailing.
Can I ask a question?
Yes.
Does that, if you go back one slide, does that hold, that presumes you can see all the way to the black hole, right? That it's transparent.
Actually, in this case, I am not showing you radiation that's directly from the black hole, but rather radiation that's coming from the gas that is being illuminated by the black hole. And so that incident spectrum creates these gas emission lines.
I said, so you don't need it to be optically thin all the way to the black hole. You're looking at illumination from within.
Right. I mean, it's not, if it was completely optically thick, we wouldn't see anything. That's true. Because then even, the gas would be blocking the internal gas that was excited. But yeah, it doesn't have to be that we can see all the way through to the black hole. There's some quantitative range in which it would work out that you could see these lines. Good question. All right, so the classification system before our work, and by the way, I'll come back to that later when we talk about a different method of detection. The classification system for our work looked roughly like this in terms of the prevailing way of doing this. That there are 3 diagnostic diagrams. Each of them involves a line ratio. And again, this is just one method of detecting AGN, but it is obviously one of the more popular because it uses optical emission, which is one of the easiest things for astronomers to study. So the y-axis is always the ratio of oxygen 3 to H beta, and then the x-axis are 3 different line ratios. I just told you about N2 and O1, both being good tracers of the presence of AGN, and S2 is another one. So these 3 line ratios are all relative to H alpha, and past work had already established, and I'm kind of cartoonizing this, so if anyone does work in this field, they'll object that, there's a line here and there's a difference between this part and this part, but just in broad strokes, the way people have divided this up is that under the lines in the blue region was star formation that was considered to be the young hot stars illuminating the gas, would produce use these line ratios, and these dots are actually galaxies showing you where real data fall on the plot. And then the red was considered to be where AGN would fall in various flavors. And the green, only in this first plot, was considered to be mixed cases. So where you would actually have young hot stars and an AGN, and both of those are irradiating the gas. And this plot on the left is the kind of original, most popular. It's called the Bpt diagram, and that is often used alone to identify AGN. But when people have these additional fainter lines, they sometimes would also use these, and that was sort of considered the state of the art. Yeah.
So does that dotted line have any meaning in the other two plots?
Yeah, it does. It gets into a bunch of jargon where, like, these are, if you know flavors of AGN, these are the Seiferts, these are the liners. People argue over just how sure they are that they really are AGN. There's a lot of details, perhaps not appropriate for this audience, but I'm happy to talk about it more later.
And it's the
Yeah.
fact that the pink and the blue region, the dividing line is roughly the same place in all three pictures. Is that sort of a test, self-consistency test of the analysis?
Oh, you have such great questions. There is no guarantee of self-consistency of this analysis, and that.
But a priori, could the lines have been in different places, or did you just fix that?
So I didn't fix this. This is what was before our work.
Oh.
And yeah, there's something kind of archaic about this, if you really think about it. In a modern era of, Bayesian modeling and data science, like, why are people just drawing a line of, measurements have error bars? There's something very crude about it. I will definitely admit to you. But these lines were drawn based on theoretical models of photoionization codes like cloudy. There's other competing codes, can create model spectra for the gas based on different illumination conditions and so on. And these lines came out of that kind of analysis, a theoretical division of like, oh, this is as far as, if you have a starburst, this is as far up as it can go. And if it's past that, it must be an AGN, that kind of logic.
It sounded like yes to me.
Well, what I'm saying
qualified,
is what I'm saying is that your question is a good one because
People argue about it.
it doesn't, well, no, people don't argue about it, but they should have,
Okay.
because it doesn't actually work. And there's not consistency, like just because something's in the red region here doesn't mean it's necessarily in the other red region. So they should have argued about it, but they didn't. All right, so with this system, past work had found that somewhere between 5 to 50% of giant galaxies were AGN or mixed, and much less than 1% of dwarf galaxies. These percentages I'm reporting out of the literature, and what people tend to do is report their percentage out of their sample. That's why this 5 to 50% is so ridiculously broad, is they'll go and they'll select a sample based on some selection criteria. And let's say, this percentage of my sample is AGN, therefore this percentage of galaxies is AGN. People are a little sloppy that way. But no matter whether it's 5 or 50, it's still much larger than the dwarf galaxies, right? So there's still a discrepancy no matter how you slice it between the dwarfs and the giants. And again, from that hierarchical buildup picture, we have to have little black holes before we can have big ones. So it didn't make a lot of sense. Where are the dwarf galaxy nuclear black holes? Oh, I have a message here we don't want. Okay. All right, so the big but here is that dwarf galaxies are uninvolved. They are, the building blocks. And so they have lots of young stars. They're mostly gas typically, and they're making stars, they're building up, and they have low metallicity. They're mostly hydrogen and helium. Again, they're not primordial, that would be too strong, but they're unevolved. And so these characteristics make these plots particularly poor for dwarf galaxies, and especially this one. So this ratio, N2/H alpha, is metallicity sensitive. And remember, this is the most popular plot that people use, often used by itself. So this BPT plot is biased against AGN in low metallicity galaxies. And when I say biased or metallicity sensitive, I'm really understating the problem, because N2/H alpha is literally used as a metric of metallicity. It is literally one of the direct metrics people use to measure metallicity. That's how sensitive it is to metallicity. So it was really not a great choice if you're looking for dwarf AGN. So this is where my work with the undergrads came in. We found a population of dwarfs with mixed classification. And I would argue that this is the discovery. So the undergrads and I together discovered a bunch of oddballs, essentially, that live here in the star-forming blue region of the Bpt diagram, but they live in the red zone of these two diagrams, the AGN region. So we call them aptly star-forming AGN. So that is apropos of your question. And so these star-forming AGN are natural hypotheses, knowing that dwarf galaxies have low metallicity and knowing how sensitive this plot is to low metallicity, is that these are just AGN in galaxies that are known to have low metallicity and tons of star formation. But we decided, let's have a prediction. So we worked with Chris Richardson on cloudy photoionization models using different mixed percentages of star formation and AGN. So these different color squares that I have overplotted on top of the data represent different mixtures of star formation and AGN, ranging from 0%, since it's a pure star forming galaxy, up to 100% AGN. And the starting point was a low metallicity dwarf with a 10 to the 5th solar mass black hole, so an intermediate mass black hole. And this is just one model. He actually ran it with a whole bunch of different metallicities and so on, but this is kind of representative of the data that we have in our survey. So we went ahead and put this one on the plot. And what you can see is that even if you have 100% AGN, no star formation whatsoever, you barely register the thing as mixed in the traditional Bpt diagram if you're dealing with a low metallicity dwarf with an intermediate mass black hole. In these other diagrams, you can get a 16% AGN out of S2, and the O1 is actually almost capable of detecting something down around 10% maybe, but 16% is absolutely cleanly detected. So, and what that means is that thing is 84% star formation in the incident radiation on the gas. So it is a highly star forming object, which is exactly what dwarf galaxies usually are. So that means that these AGN are found in typical dwarfs. There was a literature, there was a history of finding AGN in dwarf galaxies, but as best as we could tell, they were always being found in dwarfs that were less star forming, higher metallicity, like dwarfs that were kind of flirting with trying to act like a giant galaxy.
Good. How sensitive is that to the mass of the black hole?
That is a great question. We tried it, I think with 10 to the 6th, but not yet 10 to the 4th. And 10 to the 6th isn't really realistic for dwarf galaxies. So that's why we defaulted to this to show with our, in our paper. I think we do have now grids for 10 to the 4. And I do not remember, I might have it in a backup slide exactly how different they are. But I can try to come back to that at the end of the talk, because the grids are kind of gory to look at. They show like all the different possible ionization parameters and metallicities and so on.
I guess maybe what I'm driving at is that how do you change the percentage?
Oh,
How do you go
change
from
the
100 to
percentage?
0? Did you change the mass of the black hole? Do you add
No,
more
no, no,
stars?
no, sorry, no, this is all because we thought this was sort of the most likely case. We just went with 10 to the fifth for all of the simulations. And then we just varied how much of the radiation that's impacting the gas is coming from that black hole versus coming from star formation.
I see.
So you could think of it as
Okay.
either maybe changing, it's not that we actually changed the microphysics of the black hole or the star formation, but you could think of it as what that means conceptually is either you're feeding the black hole more or you're feeding the star formation more.
Okay.
Yeah.
So you said that dwarf galaxies have tons of star formation. So you're not talking about dwarf ellipticals.
Definitely not.
Are these dwarf irregulars? What kind of dwarfs are you talking about?
You two should get together. So, yeah, so the,
Andy, yeah.
so another prescient question. I want to hold off on a full answer to your question, but I will just say that these are typical dwarfs. Dwarf ellipticals are atypical dwarfs. They certainly exist, but the majority of dwarf galaxies are not satellites. A dwarf elliptical is a satellite in a system of galaxies, and satellites tend to be much less star forming for a variety of reasons I'll get into at the end of the talk. Does that,
Yeah, fine.
is that enough for
But
now?
SMC would be counted.
I'm sorry.
SMC, Magellanic Clouds.
SMC is an interesting weird case because it's only recently fallen in, and so it's not as gas poor as a lot
Right.
of other things, but it probably is somewhat gas depleted compared to, you know, a dwarf galaxy in the wild.
Okay, so those guys are even more gas rich than the Magellanic Cloud.
Yeah, because the majority of dwarf galaxies are gas dominated.
Okay.
They have
I
more
didn't know
gas
that.
than
Okay.
stars. Yeah. Mhm.
Okay.
Yeah, so I said that the discovery was as simple as finding that there are some things that live in one part of one plot and in a different part of the other plot. And you might say, well, why did it take so long to figure that out, right? Like that doesn't sound that hard. So it did not involve machine learning or any other advanced data science. We used archival data that is, you know, at least 10 years old or older. We started from the #1 classification system, very widely used and known. And dwarf AGN are a hot topic. Okay, I don't speak French, so I'm going to pronounce this wrong, but right? Because I mean, in this picture, how can you not have dwarf AGN? How can you not have black holes in dwarf galaxies, right? It doesn't make sense. So why did it take so long?
Somebody said that there are no black holes in dwarf galaxies.
Oh, lots of people have claimed. Yeah. I mean, not recently. Recently, they've been found in smattering amounts, and so nobody would claim that anymore. But
Well, I think to be fair, it's about optical detection. People have always said in the X-ray you could find them.
yeah, but they
Not
said they
as
were like
commonly.
almost vanishingly rare. Like,
Not so
yeah,
common.
like a small fraction of 1%. Like 0.3% or something like that. All right. Which is, not competing with the population in giant galaxies. All right, so my explanation, and this is now for the people who are interested in the process and philosophy of science in the room. I think there's two main things: locked in perspectives. So a lot of the people working on this problem had similar data and similar expertise. As far as we can tell, star-forming AGN were previously ignored or discarded by all of the people who should have seen them, including the people who actually made those classification systems with much bigger data sets. They definitely must have had some of these. My different data and expertise led me to pursue them and kind of forced me to not give up. And I'll explain more about that in a minute. Plus, I had a lucky team synergy in that I found, my buddy half an hour down the road who could a posteriori predict what my interpretation of the data was. That
Do
was
you think this applies to absolutely everything that ever happens?
wow. I think the historians are going to need to have a talk with you. Yeah, let me just not even answer that one. All right, and then another thing, I am talking about how 2 reasons it took so long to figure this out. I am not speaking about everything that ever happened in science. All right, so the other thing is how grant funding works. So grant funding rewards safe outcomes based on past successes on the exact same problem, however small, but incremental successes. It does not reward problem solving. It does not fund problem solving. For 5 years, my search to find an AGN diagnostic for metal poor, highly star forming dwarf galaxies involved only undergrads because they're free. And many false starts because I'm not an expert. So I tried a lot of different things that didn't work, including things that, worked but didn't work well enough, like looking at helium. Well, helium is a primordial element. So it's by definition going to be sensitive to low metallicity things, but it just doesn't pick up enough of them. So I would say that, and I apologize for those of you who are, diehard academics, that I'm bringing in a book by a journalist, but I think this is a fabulous book that everyone should read, even though it's by a journalist. It is a really good book. Range, Why Generalists Triumph in a Specialized World. This is a quote from it. Our greatest strength is the exact opposite of narrow specialization. It is the ability to integrate broadly. And a lot of times I've found in my career, that's when I go into a field I know nothing about. That's when I discover something.
But don't you
Well, that's a
really need-
great point, Sheila, because I think it's absolutely true that a person moving into a new field, this is true. And also there's a lot of disrespect for people who work on 2 sets of problems, because we are all supposed to be working on.
Right.
And that is something I have a lot of experience with, that it takes a much longer time
Yeah.
to be recognized for
Yes.
what you're doing. So if you work on dark matter and black holes, that's anathema. You should have been working on, that one thing about black holes.
I guess we could just, I can't resist commenting. I really like this quote because I think it puts down the specialists, and I think
Read
that
the
we
book.
need,
Read the book.
No, but there's, I
we,
mean,
we need the generalists and the specialists.
Right.
Maybe there's a few more specialists around, and maybe
a
we don't
lot
have the
more
perfect
specialists.
mix. Maybe we don't have the perfect mix, but I think we need everybody.
No, but we devalue the generalists, Andy, at least in astrophysics. We definitely devalue the generalists.
We not only devalue them, but we fail to understand.
But the remedy for that is not to devalue the specialists.
Well, no, but
No, we're not devaluing them.
no, I
But
think.
this quote devalues.
Wait, let me say that if you read the book, you will devalue them, because he provides a lot of studies and a lot of, let me finish my sentence. A lot of studies and a lot of evidence showing how specialists have, missed the result, missed critical advances, and then people who were non-specialists came in and found them. And he talks about a lot of different reasons why this is the case. I know it works because you're all specialists.
No, it
I
doesn't.
know.
No,
And so is
it's quite the opposite. It's quite the opposite. This is the BHI, right? We're specifically here because we're specialists, but we're all coming together
Yes.
from a very
This
broad
is
range.
your strength,
So
is
it's a
that when you
slightly
talk to each
different-
other, yes.
It's a slightly
Right.
different,
Yes.
different paradigm. You can have specialists, you can have generalists, but if you have a bunch of specialists all coming together and they're willing to work together,
Actually talking to each other.
that's
Hive
actually a
mind.
third
You got
way
your
of doing
hive
it.
mind, yeah.
Okay.
Right.
Yeah. So even though you're individually special, then this was like me working with Chris Richardson, right? I don't do cloudy photoionization models. And would I have taken the time while being a faculty member with all the teaching and, admin and so on to go and learn how to do them? Right? I mean, not that I couldn't, but right, it's just hard. So if you bring together a bunch of specialists, like you said, like you have here at the BHI, then you're capable of creating a generalist collectively together, which is awesome. So I'm very jealous of you. All right, so one of the, so the book is fantastic. It talks about a lot of different reasons why this is true and a lot of things that I won't get a chance to go into. But this is my personal story. My personal example comes from Scrabble. So my husband, who is crazy smart and 4 years older than me, used to beat me every time we played Scrabble. And you know, when you, and this was actually before we were married, when your significant other consistently beats you at something and you think you're smart, it kind of pisses you off. So I was like, what are you doing? Because like, I know I'm better at words than you are. You know, what are you doing? And he said, well, you know, I noticed you always just stare at your Scrabble tiles. I move mine. And now, you know, I've looked on the internet, this is actually just a known thing. Your brain is not capable of, you know, just imagining rearranging the data. You have to physically do it. And so you physically rearrange the Scrabble tiles, and it's so much easier to find that, you know, bonus 50 pointer, right? So much easier. So what is my equivalent in astronomy? This is where the Resolve and Ecos surveys come in. So flux limited surveys are the standard in astronomy. Why? Because when you go out and do a survey, you know, point your CCD camera at the sky for a fixed amount of time, what you get is a flux limited set of detections. And so you are going to get way more things that are intrinsically bright at larger distances, and way fewer things that are intrinsically faint because you can only sense them to relatively nearby distances. What people do to compensate for that is they correct statistically. I would argue this is like staring at your Scrabble tiles. It's not really helping your brain. What we did is, and this is showing you, this is the CFA2 redshift survey. So this orange line, or sorry, no, this, the blue is the CFA2 redshift survey. It's showing you, the blue line is a flux limited survey. That's a standard astronomical survey. And I apologize for the non-astronomers. Absolute magnitude is just a proxy for luminosity. So the most luminous things are on the right. So you can see that a flux limited survey, here is the total distribution for a complete survey of objects. And so you have, you know, tons more intrinsically luminous things and a faint tail of dwarf galaxies. Now, what we have constructed in the spirit of rearranging our Scrabble tiles is a volume and luminosity limited survey. It's a census. We have gone out and said, no, I want a box of the universe and I want everything in it, in that box, so that I can see all the relationships between all the things and the large scale structure within that box. And I want it to go down to a floor that is uniform. So, you know, if you think about an analogy, I like to give this to the ocean. If I went out and I took a giant tank and got everything in the ocean so that I could study, you know, the relationships between the different creatures in my giant tank, there would still probably be a limit below which it couldn't see. Maybe it's plankton, you know, like there's some floor, but it's a uniform floor. And in our case, it's an intrinsic property, the luminosity of galaxies, that makes this sharp cutoff. So it is a census. I don't like to call it a survey. It's a census. And that reveals that most dwarfs are metal poor and highly star forming. When you asked about the dwarf locus. When we don't do census science, we form false intuitions about dwarf galaxies because they're in the tail, right? And the false intuition that we've formed about dwarf galaxies is that they're like the ones in the local universe. Not surprising, right? And the ones in the local universe are not free dwarfs in the wild. So these are our surveys. This is the most intuitive diagram. This is a plot on the sky in right ascension and declination on the sky. This is a plot that is a little bit less intuitive, where you're at the middle for this one and This is the line of sight distance from the Hubble law, from the expansion of the universe. We figure out the distance away from us. And then this is the distance, again, along right ascension. We always have to suppress one dimension in order to look at this survey. So here for resolve, I'm suppressing what amounts to, what is that? Latitude, because it's a very thin survey in declination. I'm suppressing that and just showing you out away from us and then along the great circles along the other equatorial. And for this survey, I'm suppressing distance away from us, but both surveys are limited in their distance away from us to just a narrow range of distances away from us. So here, resolve is the black point, and I've just embedded it within the larger Sloan Digital Sky survey, which is a standard flux limited survey, and actually it goes even further. I just stopped plotting them, plotting the points, and the eco range of distance is a little bit larger, but mostly it's just way larger on the sky. So this is showing, you know, the northern spring sky for us northerners is, you know, almost half covered, but of course that's much more than half the projection. And here's one half of resolve within eco. That's this part of resolve is this long strip, and the B semester of resolve is the fall sky equatorial strip. Does that sort of make sense? Sorry for those of you who don't normally think in astronomical coordinates. All right, cool. All right, so resolve is the smaller survey. It is volume limited about 50,000 cubic megaparsecs. That is still large enough, as you can see, to pick out the cosmic web, large scale structure. There's voids, there's filaments and whatnot. It's about 1,500 galaxies, and it is ultra complete, way more complete than the Sloan redshift survey. We went to a lot of trouble to chase down things that did not have redshift and make it actually more complete. You know, they did simulations to try to predict their incompleteness, and we found more things than they thought they were missing. It is complete down to, I say 10 to the 9.x because it depends on whether you're talking about stellar mass or stars plus gas mass or, you know, various definitions. But somebody brought up the Magellanic Clouds before. It's like similar to an LMC, large Magellanic Cloud, so a large dwarf. It's a multi-wavelength census of stars, cold gas, star formation rate, environment. I mean, you know, obviously the environment is part of why we're doing it this way, to understand galaxies in their native habitat. And when I say cold gas, that's because hot gas is very hard to detect and is, you know, spread throughout the cosmic web, but the cold gas is the gas right in galaxies. And this is the plot showing the point somebody asked me about earlier. Most dwarfs are non-satellites. So here we have galaxy mass. Red is just stars, blue is stars plus cold gas, versus the group mass. So a group of galaxies, you can measure the mass of the system of galaxies. And so the big symbols are what we call the central. So it's the most luminous or most massive galaxy, depending on how you want to define it. Those are forming a relationship between the central galaxy mass and the group mass. Satellites don't have a relationship to the group mass. Satellites are little things, and so they don't have any particular correlation to the group mass. Those are the little symbols. And so what you can see is if you pick, you know, like let's say we call this a typical dwarf galaxy mass is going to be below around 9.5 or 10, depending on how you want to define it, what you want to choose as your metric. Below that, you can see the vast majority of things are central galaxies in their own small group. That we call it a group, even if it's a group of one, just because we perform like group finding on the sky, and then some things are just isolated, and we call that a group of one. So these things are pretty isolated, and they are the majority. And you can see that they're gas dominated. Look at this difference between the stellar mass and the gas mass. This is log, right? So, so typically twice or more mass once you add the gas. So, and that's the fuel for both the star formation and the AGN, right? All that gas. So ECO is a 10 times larger volume. It's less complete, but still more complete than SDSS, and it has more limited data, but we get the advantage of size. All right, so moving on in my outline, now I'm going to tell you about statistics, and this is where my graduate student came in. So we had, come up with this discovery of a new classification system, but we wanted to actually apply it to the survey, and that might sound easy, but it was not. So the first thing that she figured out, I had simplified for our press release as that greater than 80% of dwarf AGN that are found via optical plots are star-forming AGN, this new kind that we found. And I definitely oversimplified that on purpose because for a press release, you don't want to give lots of complicated numbers. But what that really means for you all, because you understand science, is that there are some caveats that I didn't want to mention about what the actual dwarf AGN percentage is. Because the actual dwarf AGN percentage is really hard to pin down. It varies from 2 to 6%. This is summing up the star-forming AGN and the traditional AGN, depending on which catalog we use. We use 3 different catalogs of measurements that are based on the same raw data. They're all based on this longitudinal sky survey spectroscopy, but people have different methods of measuring the lines. And it turns out that that systematic of how people measure the lines is non-trivial. And it's not like we didn't try to figure out, oh, which of these catalogs is more right. We couldn't. It's down to systematics that at this point in time are irreducible, I think. So that's one issue, but 2 to 6% is still, no matter how you slice it, much less than 1%, which is what was previously known, is not in the same ballpark, right? And this statistic turned out to be true no matter which way we did it. Like no matter which catalog we used, whatever dwarf AGN population we found, greater than 80% of them were these new kind. Yeah.
Right, so in the catalog, you had things that were labeled as AGNs, and then you added these extra categories of star-forming AGNs. And the extra category of star-forming AGNs contribute to 80% of the view.
Of the combined, which is what I've written here. So this is 2.9 plus 1.4 is 4.3. Hopefully, if I do my math right. Okay. And there I simplified, I put for the traditional AGN, I just put the mixed cases in with them. Because they were traditionally being identified in that place. Okay, the second caveat is that 01 plot, the third plot where I showed you was the most sensitive one. Unfortunately, the 01 line is the hardest to get. It's the weakest line. And so that limits the sample size. So in our new paper that we're just finishing up now, so I've tagged it as 2023, but hopefully maybe sooner, we'll see. We are adding back all the AGN that would be found by the BPT plot alone, just by itself, because then you're not requiring these weaker lines to exist, but it actually doesn't change things a lot. So the star-forming AGN are still at least triple the traditional ones. I mean, sorry, they triple the original numbers, what I'm trying to say. So they're 2/3 of the total. So at this point, we kind of went, yikes, like we've never done AGN science before. Nobody's going to believe us. Like this is, everybody's going to be like, who are these nobodies making this crazy claim? And if that were true, we would have it, right? Well, so we went through a whole bunch of possible counter explanations because there's very few, super specialists on this stuff in the room. I'm just going to run through this super quickly, but I'm happy to talk with any super specialists about it later. But we did, of course, look at the starburst issue, whether they could be extreme starbursts. If you've heard of a Wolf-Rayet galaxy, they're above the Wolf-Rayet locus. If you haven't, just ignore that statement. They're not as metal poor as X-ray binaries. So this is a common imposter for dwarf galaxy nuclear black holes, X-ray binaries being stellar mass creating systems that would be common in a highly star-forming galaxy. But they don't seem to fit with the model predictions there. They are rarely found in, somebody asked me earlier about that line that went off, sort of at right angles, 45 degrees. And below that, I said there were liners, and those were things that people argued about whether they were truly AGN, but they're actually not usually found there. And that also means they're probably not shock dominated. They're probably not created by shocks. And they're also atypical for a phenomenon people call diffuse ionized gas in astronomy. You can ignore all that, but the punchline is just we looked at a million possible alternative explanations because we knew, like we're not the experts, people are not going to believe us. And none of them really panned out. Like maybe there would be one individual case where maybe that case could be explained away, but not the whole population. Unfortunately, we did not find a lot of cross matches. We did find one IFU map, so like a bunch of little fibers in a bundle is called an integral field unit. So that gives you spectroscopy across the whole galaxy, and that did show us that in that one case, the O1 excess marking the where we would think the black hole is was centralized. So that was comforting. And we also found in the literature that some other folks who've been studying dwarf AGN had found things that they considered to be dwarf AGN based on radio selection, and they had made these diagnostic plots for them, and without particularly commenting on it or making a big deal out of it, you could just see that a bunch of their radio selected AGN would classify it as what we're calling SF-AGN. So, they could have found star-forming AGN, but they didn't. They just didn't flag it. In general, as I mentioned earlier, AGN percentages are typically reported relative to the search sample. And that's why those percentages are all over the map and they can't really be compared to each other. But we have census data. We can report the AGN fraction relative to the full galaxy population. And also not only a census, but a highly complete census. So that I think is pretty exciting. The theorists, at least in my field, find that to be very exciting because that's what we simulate, right? It's real boxes of the universe. And just for example, using one of the three catalogs, this is the one that happens to have statistics sort of in the middle of the other two. The star-forming AGN are 2% of all dwarfs, so that would include your dwarf ellipticals and everything. And if you add the traditional AGN, they're about 3% of all dwarfs. So now we are completely in a different league than the 0.x percentages that people were previously finding out with X-rays or whatever. And that means this is the first well-defined constraint on the dwarf AGN percentage for the full galaxy population. It's still a lower limit though, because in dwarf galaxies, the gravitational potential is weak. And so simulation suggests, and also observations, that these black holes are sloshing around. And we're just looking at the Sloan Digital Sky Survey, which put down one fiber in the middle of a galaxy. So it would be expected to miss a lot of black holes that are wandering up to a kiloparsec away from the middle. They really do slosh around. And there's also other detection methods. Now, I did want to mention for the off-center AGN, I just was at a conference a few weeks ago, or I was Zoom attending a conference that Marmez Kouas spoke at. You should totally invite her to come talk to you too. So she is using MANGA, which is an IFU, so integral field unit, all the little fiber bundle observations. It's a spin-off of the Sloan Digital Sky Survey. It's not complete in any sense. It's got a weird selection function, but nonetheless, it's cool data. And from that, she found many star-forming AGN that were off-center, including some with X-ray counterparts. So she has already used our new approach, and I found her talk very exciting. It's not published, but you should have her come talk to you. And then, the other detection methods across different bands. And so this is our new work, the 2023 paper, I'll say. I'm just showing the results in Resolve. ECO, the 10 times larger survey, is in prep. But the punchline is just for Resolve, the smaller survey, the total AGN percentage, we now have up to 7.6%. This is just blowing away any previous tally of AGN and dwarf galaxies. Nearly half of these, though, are mid-infrared detected. Mid-infrared is much more controversial. People argue whether the models are adequately ruling out star formation or not. And there's almost no overlap between the mid-infrared detections and the optical detections. But this may relate to, somebody asked me about extinction and dust. Was that you? It might relate to that because the mid-infrared AGN could be the more extincted ones, the more enshrouded ones. So it's something that bears a lot of scrutiny. But for now, here's the different categories. Traditional is the red. Notice that even our traditional number is a little bit higher. That has to be because of our sample selection, or our census approach or something. Although I will say, once we have the 10 times larger survey in there, then that statistic will be more reliable. The star forming AGN and mid-IR AGN, and then another category we added with somebody decided to redefine that first plot, the Bpt dividing line, using different models, right? You asked about the model, so they used a model they thought was more accurate for dividing AGN from star forming, and it hugs more closely, and so they get these additional green ones as counting. And so we added those in, and that gives us this 7.6% number. So now let me go on to what does this mean for black holes? Does this new census help constrain our understanding of black hole growth? Well, so the bad news, these black holes are likely to be tens or hundreds of thousands of solar masses. They're probably not seeds, and they're probably also not seeds because these are, today's dwarf galaxies. These are in the local universe, and so they will have had significant mergers and gas accretion over cosmic time. Also, as you all know, AGN are only a subset of black holes. So that's the bad news. But the good news is this is the new highest reliable limit on the dwarf black hole fraction. Because, if you've got an AGN, you think, well, that should be at least a lower limit on what the percentage of black holes is. And now that we have found these, we can start to probe accretion and feedback physics in typical dwarfs, because the previously found AGN were sort of atypical dwarfs. They were ones acting like giant galaxies. I won't go into this because it's a very messy plot, but there was this paper by Haidar et al. That's on the archive that looked at all of these major galaxy formation simulations and compared them all. And they looked at the AGN occupation fraction that was predicted by all the simulations. And then they put on a bunch of prior work on, what could be the AGN occupation fraction. And this was just for dwarf galaxies, even though it doesn't say that. And this was the range of all the prior work, and this is the range of our work. So, it is potentially capable of at least pushing the modelers to do something different. But I would argue it's not teaching us a lot because these simulations do not attempt realistic seeding. They're just not there yet. All right, then the next thing, the science context for the dwarfs. So I mentioned that star forming AGN and mid-IR AGN are in typical dwarfs. And you can see that in these plots. So for example, this is the optical color of the galaxy versus the log of its mass in stars. And here's the dwarf giant divide. And so you see the mid-IR, the orange symbols, star forming AGN are the blue. And I've actually put in both Resolve and ECO for most of the symbols, but just not the mid-IR. We don't have the mid-IR ready for ECO yet. So that's why there's fewer mid-IR. They're actually more comparable. And from this, you can see that all the way down to the bluest colors in the lowest stellar masses, the star forming AGN and the mid-IR AGN are there, but the traditional AGN, which are red, and those kind of bonus AGN from redefining the Bpt diagram and moving the line, those are the green. Those are still pushing up towards trying to be giants, and also pushing towards trying to be red, and red galaxies are more gas poor galaxies. So traditional and bonus AGN, as I said here, are massive gas poor weakly star forming. So not typical. And here is the ratio of the mass in gas to the mass in stars. So what you can see, and here it's cold gas, so it's atomic hydrogen that I'm measuring, which is the dominant cold gas component in dwarf galaxies. And it is dominant over stars below the dwarf giant divide. You can see that this is a log again, so 0 is 1 to 1. And you can see that most dwarf galaxies, by the way, the grayscale is like the full survey, and then the symbols are the AGN on top. So you can see that most dwarf galaxies are gas dominated. And that corresponds to, again, the new categories of AGN, the star forming AGN and the mid-IR detected. This is just looking at their star formation history, both short-term and long-term. And again, very highly star forming. This line represents the stellar mass doubling in the last billion years. So these are typical dwarf galaxies have that much star formation. They will have doubled their stellar mass in the last gigayear. And that dwarf giant divide, you know, might seem kind of arbitrary, but it's actually not. It comes out of galaxy evolution observations and theory. And this comes from understanding groups as systems of galaxies in a common dark matter halo. So I mentioned before that dark matter halos, when they assemble as they merge, the galaxies don't necessarily emerge immediately, right? So groups are systems of galaxies within a shared dark matter halo. And the theoretical understanding is that the next level up of gas from the cold gas that's in galaxies is something we call warm hot. So I apologize for the jargon, it's super weird, but yes, we call it warm hot gas. And that gas is warm enough to be surrounding galaxies in the halo, but it's cool enough to cool into the galaxy and replenish the cold gas that will then fuel both star formation and AGN. And that is predicted in theory, both analytic and simulation, to stop happening. The replenishment is predicted to kind of turn off as the gas heats, which happens as halos grow. And so there's 3 critical halo mass scales, dark matter halo mass scales, where you see the gas heating from the inside out. And this first scale, the threshold scale, where it first starts to heat, making it harder for the gas to cool and fuel AGN or fuel star formation, that scale corresponds to a group mass scale that corresponds to the dwarf giant divide in terms of galaxy mass. This is the same plot I showed you before. There's galaxy mass here in the upper 9s corresponding to this group mass that is the threshold scale. So basically it has to do with gas fueling that we are seeing these AGN turn on. And that means that we expect much, much more cold gas and star formation in dwarf AGN hosts, these typical ones that we're finally finding, than in normal, I won't call them normal, but familiar giant galaxy AGN hosts. We're familiar with giant galaxy AGN hosts. We would not expect them to be similar. These should have much more cold gas and star formation. And so I will expect that their feedback, their fueling is all going to be different, right? We haven't followed up yet. We haven't gotten that far, but I would expect it to be all different. And one of the key questions the theorists are asking is, you know, we think of giant AGN as exerting feedback that limits star formation. Could it actually be the opposite in this regime, where the star formation is so powerful that it limits the growth of black holes? So finally, just rediscovery. And I want to leave you with this. I think of discovery, when you discover something new about the universe, as a kind of truth and awe moment where, you know, for those of you who study philosophy, I think of like Plato's cave, where, you know, it's like you got unchained for a moment and you got to come out of the cave and actually get this glimpse of truth with a capital T, and you feel this sense of awe. And then, and then we have Feynman. I try to live by this quote, even though I'm not a huge fan of Feynman, but the first principle is that you must not fool yourself, and you are the easiest person to fool. And the scientific method, tells us no, you weren't outside Plato's cave. Pursuit of scientific truth, rejects truth with a capital T, right? We're constantly trying to figure out how we were wrong there. What did we screw up on, right? And that's what we did, right? We went through all the alternative explanations. We went through the 3 different catalogs of measurements. We tried to prove that we were wrong, but in the end, we didn't think we were wrong. And the referee asked us a lot of questions and decided we weren't wrong. And so we ended up writing a press release. And in that moment of writing a press release, it was really weird because it was like a second discovery moment. We had worked on this for so long. I told you I worked with undergrads for 5 years, another 3 years for moved as a grad student to work on all the other stuff. It's just like 8 years of being a scientist, right? And you lose that sense of awe, right? All you're doing is just trying to prove you're not an idiot. But in that moment of writing something for the public, for a press release, I felt that tingle of awe again. I was like, oh my gosh, this is real. We're going public. This is real. We really found this. And especially, that 80% stat, like when I finally figured out how to express how big this was without all the caveats. And as the news spread in like over 17 different languages, and I was just like, oh my God. I realized that, the world was sharing my sense of truth and awe about this. And it just reminds me that, astronomy is older than science. Astronomy is everything. It's philosophy, it's religion, it's a worldview. And when we share it with the world, that's when it kind of goes back to its roots. And that was kind of very profound for me. I feel like I could die happy now. So that was for the humanistically inclined among you.
Thank you, Sheila, for a very nice talk. We have time for 1 or 2 questions, maybe.
Yes.
So I know that with the X-ray, the emission lines also, in the case of an AGN, would be broadened. I don't know if in this part of the research, this is also be a good measure of deciding whether it's an AGN.
Yeah, totally. So Marmez Cloud, who I told you we should invite for talk, has been trying to look for the very small amount of broadening that you would expect from these very small black holes, because what people had been doing in the past is just looking for broadening that really stuck out, and so they would look for like 500 kilometers a second minimum. But then those were always like associated with more massive or more metal rich or whatever, like they were the unusual dwarfs. And what she's trying to do is really use very sensitive data analysis and stacking of these IFU spectra to get at stuff that you cannot see by eye, but statistically can extract. Since I'm not working on it, I don't know exactly how reliable it is, but she is detecting stuff.
Thanks for a great talk, first of all. And I was wondering, with the number that you get, I know you said it's still a lower limit for the 6% of systems Earth Mars galaxies.
Close to 8.
Yeah, close to 8.
7.9.
If you would really naively believe in the merger, the hierarchical merger scenario for these supermassive black holes, is that number still low?
Oh, totally, it's still low. But the thing is, these are just the ones that we can detect to be growing. And there might be, first of all, there might be ones that are dormant, just like our own Milky Way black hole is dormant. And second of all, there might be ones that are growing, below, I showed you 16%. Well, what if there's ones that are so outweighed by star formation that it's more like 5%, so we're not detecting those yet, right? And I think IFU surveys can be more sensitive in that sense because both they can find the off-center black holes and because they can combine up multiple pixels and get a better signals to noise. But there might be something irreducible about, like, if you have just so much star formation, you might really have to get more spatial resolution to kind of zero in on right where the black hole is. And I don't know of any surveys that are really, big enough, but also have that fine spatial resolution. But yeah, I mean, my intuition is that we're going to see, and this is just me speculating, but that we're going to see that black holes form and get kicked out and reform in dwarf galaxies. Because, there's a lot, like I said, it's a shallow potential well, and there's going to be a lot of merging and, multi-body interactions. And so my intuition, which is totally not, based
I mean,
on
that's
fact,
theoretically supported.
but-
that you
but
should
yeah.
have multiple ways of making seeds and
Yeah.
continually through cosmic time.
Yeah.
Not just very early on in the universe, but at big times
Yeah.
as well. That's where the theoretical idea is now.
so I mean, we can't really constrain this with data yet, so it's speculation. But yeah,
So early on, you made the distinction between the flux limited approach to surveys, which tends to suppress the number of intrinsically low luminosity objects.
Yeah.
Because you don't look very deep.
Yeah.
Versus choose a box and find everything in that box.
Yeah.
Right? Obviously, the second one is preferable in the sense you really find every object. But even with the first approach, what you call the statistical correction, which is just a V over V max kind of approach, which is very traditional, and why is it wrong? Okay, you
because-
get poorer statistics, but so long as you know your error estimates, shouldn't you still get pretty much the same story?
it's wrong because we're human, right? And as humans, we make judgment calls all the time about how picky to get, right? And if you have a survey in which there's maybe one or two objects that are doing this weird thing of being in one place in one diagram, in another place in another diagram, because you have such poor statistics down there that it's just one or two objects that are doing that, are you really going to expend 8 years like I did trying to figure out what that is? You just think it
And you
one,
should.
one or two
One,
objects.
but one in a
people-
small
people don't.
volume.
They did, as far as we can tell, they didn't even mention that they happened. They
Okay.
just probably threw them out as like bad data, whatever, outlier, whatever, But once you have, rearrange the Scrabble tiles, like I said, force yourself to confront these things, and you're like, there's a lot of these, dang it. I can't call them systematic errors. I can't call them outliers.
Mhm.
I have to understand that.
Okay, so it is the psychology that
I
is
think
wrong.
we're humans. We make choices, and
Okay.
We should probably conclude it here. We can continue our lunch. So let's thank our speaker again.
refer to the